All right, Chemistry 1411. This is the practice ACS style exam. And we're going to begin by taking a look at question number 1. And since there's not a lot of room on this document, I'm going to be solving most of the problems from a blank screen. So I'm going to switch over to a blank screen now. And let's take a look. So question number 1 asks us, which pair of particles has the same number of electrons? We have fluoride and a magnesium ion. Then we have neon and argon. Then we have a bromide ion and selenium. And last we have aluminum, an aluminum cation and phosphide. P3 minus is called phosphide. Well, if we look at a periodic table, and you should always have a periodic table handy whenever you're doing practice problems in chemistry class. So if I look at fluorine, it's in group 7A. It's in the second period. If I have fluoride, I have to add 1 electron. And so fluoride has 10 electrons. If I look at magnesium, it's element number 12. But when I have a 2+ charge, that means I've lost 2 of those 12 electrons. So I have a total of 10 electrons. Right away, we can see that A is the answer. If we look at the next one, neon and argon, we just look at neon. Its atomic number is 10. It's got 10 electrons. Argon is element number 18. It has 18 electrons, so that is not the answer. Bromide, if you look at bromine, it's element number 35. If we add 1 electron for the negative charge, we get 36 electrons. Selenium is element number 34. There's no charge, and so it's got 34 electrons. Aluminum 3+. Well, aluminum is element number 13. If we have a 3+ charge, that means we lose 3 electrons, so we have 10 electrons. And for the phosphide, again, this is called phosphide, P3 minus. We have phosphorus, which is element number 15. We would add 3 electrons because we have a 3- charge, and we have 18 electrons. And so the answer is A, the fluoride ion and the magnesium 2+ ion both have 10 electrons. Let's move on to the second question. The second question says, how many neutrons are there in this isotope of chloride? Keep in mind this is chloride, not chlorine, because it's got a -1 charge. So how many neutrons are in this isotope of this anion? Well, you should remember that this number up here, this represents the mass number, which is equal to the sum of the number of neutrons and protons. And this number down here, this is the atomic number, which just equals the number of protons. So if 37 is equal to the number of neutrons and protons, and I know the number of protons is 17, I take 37 minus 17 and I get 20, which is equal to my number of neutrons. And 20 is answer B. So 20 neutrons and that isotope of chloride. And again, you have to know what a mass number is, and you have to know what an atomic number means. All right, let's move on to question number 3. And again, stop me at any point if you have any questions. I'd be happy to do my best to answer them. Question number 3 is a math problem. You're going to need a calculator for this one. And of course, you're allowed to bring in your calculator to the final exam. And there's a couple of ways that you could solve this problem, but I'll show you the foolproof method. It says bromine has 2 naturally occurring isotopes. We have one isotope that has a relative abundance of 50.69%, and that's bromine 79. So this is bromine 79. And it says the mass of bromine 79 is 78.9183 atomic mass units. And it's asking us, what is the other isotope? What is the other isotope? Well, you can see that the bromine 79, its atomic mass is pretty close to 79. 78.1, it's only a tenth away from 79. And so we can infer that if we figure out the mass of the other isotope in atomic mass units, it's going to be close enough, or very close, as a matter of fact, to the mass number. Okay, so let's take a look here. And again, you could probably solve this one in your head conceptually, really. It's conceptually or quantitatively to some extent, but I'll show you the foolproof method because this is how we did it in General Chemistry 1. If you go to your periodic table and you look up the atomic mass of bromine, you see that bromine on the periodic table is 79.90 AMU. Okay, it's that many atomic mass units. Now, if we have 2 isotopes and the relative abundance of the first one is 50.69%. We're going to say in a fraction of 1, I have 0.5069 times this mass, 78.9183 AMU, like that. Now, what's the other relative abundance? Well, if I have a total of 100% and I subtract 50.69%, I'm going to be left over with the relative abundance of the other isotope, which is going to be, it is 49.31%. So now I can say that 0.4931 of a fraction out of 1 is going to be multiplied by the atomic mass of that second isotope. That's going to produce the atomic mass that I see on the periodic table. Because remember, the atomic masses that you see on the periodic table are weighted masses, right? Based on the relative abundance of the isotopes. And here we have 2 isotopes. So now all we have to do is solve for this value of X. So I'm going to do a little bit of the simplification here. I got this 79.90 is equal to 40.00369. And I know I'm carrying extra sig figs. I'll round them off at the end. Plus 0.4931x. Okay. And that gives us 0.4931x. Just some simple algebra is equal to 39.89631. Again, carrying extra sig figs. We divide by this number, 0.4931, in order to solve for x. And we get that our x is 80.91 AMU. Now, our mass number is going to be a whole number. It's not going to have a decimal. And so 80.91 is only 0.1 units away from 81. So it's going to be bromine 81 will be the other isotope. And that is answer D. And again, this is the type of problem that we looked at quite a few times in General Chemistry 1. I know I asked a question like this on the exam if you were in my 1401 class. And the whole idea is that you understand where the masses come from on the periodic table, that you understand that they are weighted averages of the relative abundance of isotopes. All right, let's move on from there. Take a look at question number 4. Question number 4 asks us which of these species is or are paramagnetic. So 4 says which are paramagnetic. And what does paramagnetic mean? It means it's going to have unpaired electrons, and it's going to be attracted to a magnet or a magnetic field. We'll just put magnet to make it simple. There we go. So we're looking for elements or ions that have unpaired electrons. And we've got titanium with a 4+ charge. We've got iron with a 2+ charge, and we've got zinc with no charge. Well, let's start with the titanium. If we look at titanium 4+, okay, find titanium on the periodic table. It's element number 22. You see that titanium has an electron configuration of argon 4s2 3d2. So if it loses its 4 electrons, it's going to lose the 2d electrons and the 2s electrons, and then it's going to be isoelectronic with argon. Right? If it's isoelectronic with argon, argon is a noble gas and it has no unpaired electrons. So that means it's going to have no unpaired electrons, and so it's going to be diamagnetic. So this will be diamagnetic. It means it's not going to be attracted to a magnetic field. It'll actually be slightly repelled by a magnetic field. If we take a look at iron with a 2+ charge, well, if we look at the electron configuration of iron, iron would be argon 4s2 3d1 2 3 4 5 6. But you remember the first in and first out rule is that if we have the 4s2 and the 3d6, when we remove 2 electrons to make a 2+ charge, we remove the electrons with the higher principal quantum number. We remove the 4s2 electrons. And so the electron configuration of the iron 2+ is argon 3d6. Well, if I look at my 1, 2, 3, 4, 5 3d orbitals, I have 1, 2, 3, 4, 5, 6 electrons in them. That means I have 1, 2, 3, 4 unpaired electrons, and therefore this one is going to be paramagnetic. It will be attracted to a magnetic field. So this one is one of the possible answers. If we move on from there and we look at zinc, so zinc, where is zinc in the periodic table? It's element number 30. You see that zinc has an electron configuration of argon. Its 4s shell is full, 4s2, and its 3d shell is completely full. Right? There are 5d orbitals, just like we saw here. Each orbital can hold a maximum of 2 electrons, so all electrons are paired. Therefore, zinc is diamagnetic. Magnetic. We'll just go like that. And so the answer to the question is A, and it's iron 2+ only. That's the only one that is going to be paramagnetic, will be attracted to a magnetic field. Let's move on to question number 5. Question number 5 says, and again, I'm just following along here on the exam, and I'll try to write down some of the details as we go. It says you have these 3 species. You've got a fluoride ion, a magnesium ion, and a sodium ion. And it says they all have the same number of electrons. Okay? They all have 10 electrons. It doesn't tell us that in the problem, but we can figure that out. They're all isoelectronic with neon. Which is the predicted order when they are arranged in order from of decreasing size? So we go from largest to smallest. Could anybody tell me which one of these would be the largest ion? Which one would be the largest? If they all have the same number of electrons. All right, I'm getting some different answers here. But if we think about this, okay, the fluoride ion has an extra electron. What does that cause? That causes electron-electron repulsion, right? And so those electrons are going to be repelling each other. Also, if you look at the atomic number, you go from fluorine, and I'll just write the atomic numbers below, right? The atomic number of fluorine is 9. The atomic number of magnesium is 12, and the atomic number of sodium is 11. So look, not only does the fluoride have a negative charge, right? It's got an extra electrons. It has the least number of protons. And therefore, those electrons are going to be reined in the least out of all of these ions, right? It has the weakest nuclear charge. And therefore, the fluoride is going to be the largest of all of them, right? Then if we compare the cations, you remember that as you have more and more positive charges, what are you doing? You're removing electrons, right? If you go from a +1 to a +2, right? You have 2 electrons removed, but you even have more protons in the magnesium nucleus than you do in the sodium nucleus. So look, you've got more charge in the nucleus, okay, and you've got less electrons for them to pull on. Therefore, they're going to pull those electrons, those 10 electrons, in even tighter. And so magnesium 2+ is going to be the smallest of all of them, and the sodium cation will be somewhere in the middle. And so the answer is D, that fluoride is the largest, followed by the sodium cation, followed by the magnesium 2+ ion. Again, this is General Chemistry 1. Let's move on to question 6, which deals with the electronic structure of the atom. It says, which electronic transition in the hydrogen atom is associated with the largest emission of energy? And I'm going to write down the answers here. Largest emission of energy, we've got N is equal to 2 to N is equal to 1. We've got an N is equal to 2 to N is equal to 3. We've got an N is equal to 2 to N is equal to 4. And we've got an N is equal to 3 to N is equal to 2. Is there any of these that we could remove immediately? Is there anyone that strikes anybody and just says, well, these cannot be possible answers? Yeah, okay. Warren's got an answer. Does anybody else have an answer besides Warren? Warren, you're definitely in the right vein. Yes. Okay. So Joey says B and C, and I agree. Yeah, B and C, we can scratch those out immediately, right? Why? Because these two are not emission; these are absorption. Absorption. Because we're going from an N low to an N high, right? We're going from low energy, or yeah, lower energy to a higher energy, and so therefore those are absorption, right? We're going from a lower energy level to a higher energy level. Whereas A, we're going from a high to a low, and in D, we're going from a high to a low, right? We're going to, these are going to be emission because we're going from a higher energy level to a lower energy level. And so energy will be emitted. All right. So with that in mind, if we compare these two, hopefully you'll remember the relationship between the N values and the amount of energy. Now I'll just summarize it here for you. So the smaller N's are going to result in a greater change in energy, okay? For the same amount of steps, right? Here we're going from, we're having a difference in N of 1, right? We're going from 3 to 2, and here we're going from 2 to 1. So they're both a delta N of 1, right? But you remember that when we talked about the difference in energy levels, right? And this is a figure that's in our textbook or something like it. We go from N is equal to 1 to N is equal to 2 to N is equal to 3 to N is equal to 4, N is equal to 5, right? And they get smaller and smaller. So the lower the number, the bigger the energy transition. Okay, now if you need to just work out the math on this one, you could do that too, and you'll end up with the right answer. Right? If you decide to use the formula that delta E is equal to the Rydberg constant divided by 1 over the N initial squared, subtract 1 over the N, the N final squared. Let's just do it for A. And when you do that, you get 2.18 times 10 to the negative 18 joules multiplied by 1 over 2 squared, subtract 1 over 1 squared. So that's 0.25, subtract 1. So that gives you negative 0.75. And you get a delta E that's a negative value, right? Because it's emission. And you end up with negative 1.64 times 10 to the negative 18 joules. Now that's for A. So this is for A. And A is the correct answer, right? Because we know that the smaller the N's are, the greater the amount of energy. Well, if we try the same thing for D, so I'll just write it here. When we do this for D, you'll find that your delta E in this case is equal to negative 3.03 times 10 to the negative 19. Times 10 to the negative 19 joules. And that is a smaller number. And so the answer is the most amount of energy, or the largest emission of energy, is going to be from the N is equal to 2 to the N is equal to 1 energy level. If somebody has their microphone on, if you could turn it off, that would be great. All right, let's move on from there. Let's take a look at question number 7. So where I am right now is we finished 1, 2, 3, 4, 5, 6. Now we're on to question 7, which deals with ionization energies. So what's an ionization energy? It's the amount of energy required to remove one electron from an element in the gaseous phase. So which pair of elements is listed in order of decreasing first ionization energy? So let's go back to our blank document and see if we can't solve this one. All right, so let's take a look at the pairs of elements that we have. Let's see, what do we have here? We've got sodium and magnesium. So sodium and magnesium in that order. Then we have magnesium and aluminum. Then we have aluminum and silicon. And then we have, in D, we have silicon and phosphorus. You know, I'm writing these down and notice something in common with all of them. If you look at the periodic table, you see that sodium and magnesium are right next to each other. right? They're right next to each other. If you look at magnesium and aluminum, magnesium is in group 2A, okay? And aluminum's next to it. Technically, it's in group 3A. So aluminum. If you look at aluminum and silicon, they're right next to each other. They're in group 3A and 4A. And then if you look at silicon and phosphorus, right, silicon's in group 4A. And phosphorus is in group 5A. So they're all close to each other, right? But there's one that's an anomaly here, okay? And that is when we go from magnesium to aluminum, right? If you look at the blocks that these elements in, right? Sodium and magnesium are both in the S block, right? Aluminum and silicon are both in the P block. Silicon and phosphorus are both in the P block, whereas magnesium is in S and aluminum is in P. Now again, ionization energy of magnesium, let's say, that's the amount of energy that's required to remove one electron from the magnesium in the gaseous phase, and the amount of energy required to remove one electron from aluminum in the gaseous phase. So it's asking which ones are in order of decreasing first ionization energy. Well, the rationale is this. As you go from left to right across a period, ionization energy generally increases. Ionization energy increases. Why is that? Why does it cost more energy to remove an electron from a fluorine than it does a lithium? Well, in part, it's due to effective nuclear charge, but it's also due to the size of the atom, right? We know that atomic size decreases as we go across a period. And so the electrons are more tightly held. Now, the reason that this one is an exception, okay, is because in magnesium, the two valence electrons are both paired up in an s orbital. If you take a look at the electron configuration for the valence electrons of magnesium, it's neon and then 3s2, right? Both of those electrons are paired up in a 3s orbital. Whereas if we look at aluminum, we have neon, right? Then we have 3s2, 3p1. So you have the 3s orbital that's got two electrons in it. Then you've got the 3p orbitals that has only one electron in it. And so it's actually easier to remove this electron that isn't paired, that's unpaired in this p orbital. And if you're wondering, when did we cover this? This is actually one of the exceptions that we looked at. And in the ACS final, they don't just leave out every exception. Some exceptions are important in chemistry class, and this is one of the exceptions that would have been covered in General Chemistry 1. So there's an anomaly here when we go from the magnesium to the aluminum, and I'm trying to give you the rationale for it here. All right, let's move on to question number 8, just a nomenclature problem. I like to solve these problems by writing down the formula. It's asking me, what's the formula of barium? Barium phosphide. I'll also point out that there's a mistake in the answer key, and I'll show you what I mean here in a second. But let's just see if we can name barium phosphide. Barium is found in group 2A. It's element number 56. So barium is going to form a +2 charge. Phosphide, I've covered phosphide this morning a little bit. You know that nitrogen with the 3- charge is nitride, right? N3-. That's called a nitride. So if we have P3-, that's a phosphide, okay? P3-, it's isoelectronic with argon, so P3-. Now, how do you combine these? You can use the old trick that's probably in the textbook here where you cross these, then you'd have barium 3 and then P2 like that. I mean, that's one way of doing it, and that is the correct answer. I like to just say, well, if I have 3 of the bariums, I have +6, and if I have 2 of the phosphides, I have -6, and so that would be the correct answer. Now, if you look at the if you look at the key, and this is a mistake I noticed yesterday when I was doing this. These two, I don't know where the calciums came from. I don't know if somebody, where this came from, but these are incorrect. This is not even, reasonable answer. So this would be Ba2, P3 is what I meant to put here. And then this one would be Ba3, P2. All right. And so the answer is D. Okay, would be the Ba3P2. And again, I apologize for that little error there. Okay, let's move on to question number 9. How many valence electrons are in carbonate? Good gravy. I bet you my students could solve this problem faster than I can. So let's take a look here. We have a carbonate ion, CO3 2-. You have to know your polyatomic ions in general chemistry 1 and 2. They come up almost Avogadro's number of times. So valence electrons in a carbonate ion. So we have CO3 2-. So if CO3 2-. Well, from the carbon, it's in group 4A, so we have 4 valence electrons. Oxygen is in group 6A, and I've got 3 of those. Then from the -2 charge, or the 2 negative charge, I have 2 more electrons. So that gives you 6 times 4, which equals a total of 24 electrons, which is C. Just tallying up valence electrons, right? That's something that we would have done a lot when we were looking at Lewis structures, especially in resonance and things like that back in general chemistry 1. All right, question number 10 is a question about oxidation numbers. Question 10 just says oxidation number of titanium in titanium I'm not going to tell you the name of the compound because that'll give it away, right? Well, the oxygen, you know that oxygen almost always has a -2 charge, except for in compounds like hydrogen peroxide. Very well, you can have superoxides and things like that, but that's neither here nor there. But we've got 2 of these, so that means we have a -4 charge. So that means that our titanium, if this has a 0 charge overall, -4 plus +4 equals 0. And so the oxidation number of my titanium is +4, which is D, right? That's something that everybody should be able to do, is calculate an oxidation number. All right, let's move on to a question that deals with balancing reactions. So this is question number 11 in the practice ACS style exam. It says, what is the coefficient for zinc oxide when the reaction is balanced with the smallest whole number coefficient? So we have zinc sulfide. Remember, zinc is one of those transition metals that only has 1 oxidation number. It's always +2, so it's not zinc 2 sulfide, it's just zinc sulfide. Plus oxygen produces zinc oxide plus sulfur dioxide. Now, remember that the trick I taught you when it comes to balancing these types of equations is that if you have an element by itself, that's like your ace up your sleeve, right? You save that until the very end. So let's take a looky. We've got 1 zinc over here. We've got another zinc over here. That's balanced. We got 1 sulfur here. We have a sulfur there. Everything's looking good. We have 2 oxygens, but I said we'll save that till the very end. But on this side over here, we have a total of 1 in the zinc oxide and 2 from the sulfur dioxide. That means we have 3 oxygens on this side, right? 3 oxygens. Now I have O2. Something times 2 is equal to 3. What would that thing be? Right, that thing would be 3 over 2, like that. So now that we have that, the question is asking us, what's the coefficient of the zinc oxide, when everything is balanced with smallest whole number coefficients? That means we have to take this entire equation and we have to multiply it by 2. That gives us 2 zinc sulfides plus 3 oxygens produces 2 zinc oxides plus 2 sulfur dioxides. You can double check to make sure that everything is copacetic, and you see that the answer is B. 2 is the coefficient that ends up in front of the zinc oxide when everything is balanced with the smallest whole number coefficients. Let's take a look at question number 12. What's question number 12 about? All kinds of stuff. It says you have an initial reaction mixture that has oxygen and fluorine. Let's go back to the actual exam itself because we need to look at the pictures here. So this is question number 12. It says you've got an initial reaction between oxygen and fluorine shown over here. So this is the reaction. Okay, looks good. I got my oxygen O2 molecules, which are the little 2 white spheres together and the 2 black spheres together. Those are my fluorine molecules. Good, good. Which representation shows what would be present after the reaction is complete? Now, it tells us we're starting with oxygen plus 2 moles of fluorine gives you 2 moles of oxygen difluoride. Well, if we make an ice table for this, I think that's the best way to solve this kind of problem. We have our O2. Let me choose a different color here. We have O2 plus 2 moles of F2 produces 2 moles of OF2. Well, how many moles of oxygen are we starting with? We've got 1, 2, 3, 4, or 4 particles, if you will, not moles. We'll just say we have 4 particles of oxygen. We've got 1, 2, 3, 4 particles of fluorine, and we have no OF2, right? What would the OF2 look like? Well, if the oxygen is a white sphere and the fluorine is a black sphere, it should look something like this, right? So that immediately, if this is our OF2 molecule here, then we can immediately get rid of this thing. I don't even know what that is, right? We can get rid of this guy too. So then it boils down between B and D. You can see that we have some OF2 molecules in both of them, but what's the difference? In B, we still have oxygen left over. Does that make sense? Okay, well, let's see. If we consume all of the fluorine, right, and we consume twice as much fluorine as we do oxygen, that means we're only going to lose half as much oxygen, right? And if we have a 1-to-1 ratio, or 2-to-2 ratio, if you will, for the fluorine to the oxygen difluoride, that means we're going to gain 4 molecules of this. Now, what's going to be left over at equilibrium? You're going to have 2 molecules of oxygen, you're going to have none of the fluorine, and you're going to have 4 molecules of OF2. Look at this. We've got 1, 2 molecules of the O2, and we've got a total of 1, 2, 3, 4 molecules of the OF2. And so B is the correct answer. D is just way off in left field because there's no oxygen left. No O2 present. So that cannot be correct. All right, so the answer is B. All right, let's move on to question number 13. I'm going to move back to my blank document to solve this one. This is one that I would expect everybody in the class to get correct and very quickly. And if you notice, some of the questions on the exam, I don't like to use the word simple in chemistry class, but I would say this would be one of the lowest level questions that you would find in a university level chemistry class. Let me go back to my blank doc here. So let's see, there we go. So number 12, the answer was B. And let's move on to number 13. So we have 1.75 moles of zinc, and then we're looking for the mass. Mass equals something. Okay, well, if I have 1.75 moles of zinc, you know that the atomic masses on the periodic table represent the number of grams per mole as well. If I go over to my zinc on the periodic table, zinc is element number 30. I see that zinc has an atomic mass of 65.39 grams of zinc in 1 mole of it, like that. So moles cancel. I punch that spinach into my calculator. I should have a total of 3 sig figs for my final answer because I only have 3 sig figs here. And I get 114 grams, which is D. That should be a pretty routine calculation for you by now. Let's move on to question 14. This is a problem that we looked at several times in General Chemistry 1. I think it was either on your first or second exam. The question reads, what is the empirical formula for a compound comprised of 54% sodium, it's 8.50% boron, and it is 37.5% oxygen by mass? So we're going to end up with some formula that is sodium X, boron Y, and then we'll put oxygen Z like that. But we need to find out what the molar relationships are, right? If I look at a compound like glucose, C6H12O6, what do those subscripts represent? Those represent the molar ratios, right, of each one of those. Or they represent, actually, in this case, it doesn't represent the molar ratios, does it? Because that's not an empirical formula. So if I write CH2O, that represents the molar ratios, 1 mole of carbon for every 2 moles of hydrogen for every 1 mole of oxygen, like that. So that's what we're trying to figure out, is what's the empirical formula for this compound. So what's the assumption that we have to make here, right? What we're going to do is we're going to assume we have a 100-gram sample. right? That means that I would have 54 grams of sodium, 8.5 grams of boron, and 37.5 grams of oxygen. Well, if I know the mass of each one of these, I can figure out the number of moles, can't I? Let's see if we can do that. So we have 54.0 grams of sodium divided by 27.99 grams per mole of sodium, and we end up with 2.34 moles. That's for our sodium. For our boron, we have 8.50 grams divided by the molar mass of boron, which is 10.81 grams per mole, and we end up with 0.786 moles. We do the same thing for the oxygen. We have 37.5 grams divided by 16.00 grams per mole of oxygen, and we end up with 2.34 moles. So right away you can see that the ratio, the number of moles of sodium to boron is going to be sodium to boron. No, sodium to oxygen is going to be 1 to 1. So what's the next step? The next step is we're going to divide all of these molar quantities by the smallest quantity, which is 0.786. So we do it here, 0.786 moles, and we end up with number 1, of course. Here we have 0.786. Now I've gone ahead and done the math here, and I got 3.06, and then I did it here, 786 moles, and I ended up with 2.98. Okay, now these are close enough, right, that they're close enough that they look to be about 3, and this one's about 3. So if we put all that spinach together, what do we get? We get Na3, 1 boron, and O3 like that. So that would be our final answer, which is B. All right, give me a thumbs up if you follow me on that question, and stop me if you have a question about that problem. That's one that we looked at several times in General Chemistry 1. Even if you didn't take the class with me, you would have seen that problem more than once. I'm sure you would have seen that on an exam or a practice problem or something. Very common problem in General Chemistry. Let me just take a look at something here. All right, so let's move on from there and take a look at question number 15. Question number 15, it says 25 grams, so we've got 25.0 grams of CO2. Then it says it contains how many oxygen atoms? Okay, and they tell us the mass of CO2 is equal to 44.0 grams per mole. I bet you there's people in the class that have that memorized. If you do enough practice problems, you tend to get that memorized pretty quickly. All right, well, we're starting out with 25.0 grams of CO2. Let's see if we can't solve this by dimensional analysis. We know that in 1 mole of CO2, we have 44.0 grams of CO2. If we were to stop right here, all we would have is the number of moles of CO2, but we want the number of oxygen atoms. I know that in 1 mole of CO2, I have 2 moles of oxygen, don't I? 2 moles of oxygen. Now remember, if I have CO2, right, as a whole, 1 mole of that whole thing, but there's 2 oxygen atoms in it, so I have 2 moles of oxygen atoms for every 1 mole of CO2. Okay, so that gives us our second conversion factor. Now if we were to stop, we would just have the number of moles of oxygen, but luckily I know that in 1 mole of oxygen, I have 6.022 times 10 to the 23rd power atoms of oxygen, like that. And that gives us the number of atoms of oxygen. So if we punch all that spinach into our calculator, which shouldn't take very long, we should have 3 sig figs in our final answer. And I got 6.84 times 10 to the 23 atoms of oxygen. And I'm going to say that there might be another error in here, a rounding error, because answer B is the only one that's reasonable, 6.80 times 10 to the 23rd power. But I don't think I did any rounding errors. So there we go. B is the correct answer. All right. And again, you'll never see an answer that's, a thousandth off or something. You know, I'm never going to give you answers like that to kind of throw you off the trail. Like, oh my goodness, do I have to practice rounding things off in my calculator? Never did it before. Not going to start doing it now. Okay. All right. Let's move on to question number 16 in the ACS style practice exam. It says, what mass of iron 2 sulfide is required? So this is question number 16. To form 1.08 grams of iron 3 oxide with excess oxygen. So if you didn't follow what I just said, here's the question. Let me write down the balanced equation. We have 4 moles of iron 2 sulfide plus 7 moles of oxygen produces 2 moles of iron 3 oxide plus 4 moles of SO2. And what they're saying is, if you want to form 1.08 grams of this guy, iron 3 oxide, it says, what mass of this do you need? How much iron sulfide? And you can just assume that you have this in excess. You got all the oxygen that you would ever need at your disposal. Well, what do we need here? We're going to have to do a little bit of dimensional analysis. Now, in the problem, they've actually gone ahead and helped us out by giving us some molar masses. They said that the molar mass of iron 2 sulfide is 87.92 grams per mole. That of iron 3 oxide is 159.7 grams per mole. And we're going to be able to use that to help us speed up the problem solving process a little bit. Now let's start it with what we know. If we want to make 1.08 grams of iron 3 oxide, we know that in 1 mole of iron 3 oxide, we've got 159.7 grams of iron 3 oxide. Now, if I was to stop right here, and I know I do this a lot, but all we would have is the number of moles of iron 3 oxide. In order for us to figure out the mass of iron 2 sulfide that we need, we're going to need the number of moles of iron 2 sulfide, won't we? But we can use this beautiful balanced equation that's been provided to us, because we know that for every 2 moles of iron 3 oxide that gets produced, we consume 4 moles. I left out my units here, didn't I? 4, just getting carried away here. There we go. 2 moles. I have 4 moles of iron 2 sulfide being consumed. Now, if I want the mass of my iron 2 sulfide, I know that in 1 mole of iron 2 sulfide, I've got 87.92 grams of iron 2 sulfide, like that. Look at this. This is beautiful. The moles of iron 3 sulfide cancel out. The moles of iron 2 sulfide cancel out. And what am I left over with? Grams of iron 2 sulfide. The mass that I would need to have in order to produce 1.08 grams of iron 3 oxide. This is assuming 100% yield, isn't it? But we like to make that assumption a lot in general chemistry. So we end up with 1.19 grams of iron 2 sulfide, like that, which is C. Here we go. So a little bit of stoichiometry here. The next question, number 17, deals with units of concentration. This is problem number 17. It says you have a 750 gram sample of drinking water, and it's found to contain 4.4 milligrams of lead. It wants us to determine the concentration of Pb in parts per million. Well, this is just going to simply force you to recall parts per million is being the mass of the analyte or the solute. Okay, maybe I'll change it to mass of solute. That might be better. We'll put here. Come on. The mass of the solute in grams times 10 to the power of 6, right? Because we're dealing with something that's very dilute, divided by the mass of the sample, or we'll put here the solvent in grams, like that. So if we work this out in parts per million, we have the mass. Now our mass is 4.4 milligrams, which I would say is the same thing as 4.4 times 10 to the negative 3 grams, right? Because we know that in 1 gram we have 1,000 milligrams. So I'm just doing a little mental math here. So in order to simplify it, the way that I did it was this. I said, well, what if you take 4.4 times 10 to the negative 3 grams, and then we multiply all that by 10 to the power of 6, right? Which just gives us 4.4 times 10 to the 3, but whatever. It's a faster way of doing it, in my opinion. You divide all that by 750 grams, and you end up with 5.9 parts per million. Is that one of the answers? Yeah, it's A, 5.9 parts per million. Let's get back to another problem that deals with stoichiometry. Right now, we're on question number 18 in the practice exam. It says, consider this reaction of lead. You have 2 moles of lead 2 oxide plus 1 mole of lead 2 sulfide produces 3 moles of lead and sulfur dioxide gas. What's the theoretical yield that can be attained by the reaction of 57.33? So I've got 57.33 grams of the lead 2 oxide and 33.80 grams of the lead 2 sulfide. What kind of problem is this? This is a limiting reactant problem, isn't it? We have to do all the stoichiometry for the 57.33 grams of lead 2 oxide, assuming that we have all the lead sulfide in the world, and then we have to do the same thing for the lead sulfide. So pitter patter, let's get at her. Takes a while to solve these guys. So let's see here. I'm running out of space here in my blank document. All right, so this is question number 18. Let's start by writing out the balanced equation. Question number 18. So we have 2 moles of lead 2 oxide plus 1 mole of lead 2 sulfide produces 3 moles of lead plus 1 mole of sulfur dioxide. Anyhow, we're starting out with 57.33 grams of the lead 2 oxide, and we're going to try the same thing with 33.80 grams of lead 2 sulfide. And then we want to figure out what's the lowest yield out of both of these, right? Because it's a limiting reactant problem. Let's start with the lead 2 oxide first. If we start it with 57.33 grams of lead 2 oxide, we'll use the molar mass. 1 mole of lead 2 oxide has a mass of, and this is given to you in the problem, it's 223.2 grams of lead 2 oxide. Now, again, if we were to stop here, we'd end up with the number of moles of lead 2 oxide, but I want to know the mass of lead. So I can go to my balanced equation and I say that for every 2 moles of lead 2 oxide that was produced, or consumed rather, I produce 3 moles of lead, but that doesn't tell me the mass of lead, does it? But I know that in 1 mole of lead, I have 207.2 grams of lead. And of course, you can get that from the periodic table. So we have moles of lead 2 oxide canceling, we have moles of lead canceling, and we end up with grams of lead in the end. When we punch all that spinach into our calculator, I got 79.83 grams of lead. Now we do the exact same exercise, but for the lead 2 sulfide, I'll go a little faster this time. We have 33.80 grams of lead 2 sulfide in 1 mole of lead 2 sulfide. I have 239.3 grams of lead 2 sulfide, and of course, that information was provided in the problem. I know that for every 1 mole of lead 2 sulfide, looking at my balanced equation, for every one of these, I produce 3 moles of lead. So 3 moles of lead, but I need the mass of lead, and I know that 1 mole of lead has a mass of 207.2 grams of lead. Little dimensional analysis, right? Grams of lead sulfide cancel. Moles of lead sulfide cancel. Moles of lead cancel. And we're left over with grams of lead. Looks good. When you punch that into your calculator, you end up with 87.80 grams of lead. So could anybody tell me which one of these is the limiting reactant? Is it the lead 2 oxide or the lead 2 sulfide? Yeah, thanks, Jamil. It's the lead 2 oxide. So this is our Let me get this out here. This is our limiting reactant, right? Because this one gave us the smallest number, right? This one gave us 79 or 80 grams. This one gave us almost 88 grams. So since this number is lower, that means that the lead-2 oxide is the limiting reactant, and this is the maximum amount of lead that you could produce, is 79.83 grams, which is answer C. It's just like if you took my General Chemistry 1 class, we talked about, I don't even remember exactly, but I know we had the hot dogs and the buns, and we were trying, or the wieners and the bun, I don't remember. But anyhow, and then I had another example, which I was trying to make a sundae or something, and we had ice cream scoops and cherries. I can't put it all together right now, but hopefully those kind of things help or help you understand limiting reactants. Let's take a look at question number 19. You know, I don't like to use the word simple in a chemistry class, and I say that all the time, and I really don't like to, because chemistry is not an easy subject. It's one of the what we call hard sciences. Question 19, though, is one I would expect everybody to get. We have 8.56 grams of sodium acetate. So what's sodium acetate? It's NaC2H3O2. That's the acetate ion. It tells us the molar mass of sodium acetate is 82.03 grams per mole. It says you have 750 mils of water. You're diluting to 750 mils. Gives us 4 sig figs there. And it says, what is the concentration of the solution? That's it. 8.56 grams of sodium acetate put in 750 milliliters of water. Well, you know that concentration and molarity is equal to the number of moles per liter. How do we figure out the number of moles of sodium acetate? We have the mass, 8.56 grams. We have the molar mass, which is 82.03 grams per mole. Just per mole, like that. And then we divide that by the volume in liters. 750 milliliters. If we convert that into liters, remember that in 1,000 milliliters, we have a liter. So we're going to divide that by 1,000, and we end up with 0.7500 liters. So this is a one-stop shop. We got everything in there. We end up with moles per liter, and we find out that our concentration is equal to something. It's equal to 0.139 molar, like that. And that is answer B. So just a simple calculation of concentration. Everybody here should know how to calculate concentration.